So yes, any questions? You should be asking more questions. Now, last week we started discussing the dielectrics in the last few weeks. And the idea was if you have any material, if you put it in an electric field, the electric field will modify the charges inside the dielectric, and hence the dielectric itself will have a non-zero dipole moment, which we use the polarization to describe this dipole moment density. And once we know this polarization, it basically corresponds to some charge distribution created by the bound charges in the system. And we said that these bound charges has this volume charge density given by the divergence of this polarization, and also a surface charge density given by the normal component of this polarization. And hence, since we know now if we know the polarization, then we know these charge densities, and starting from these charge densities, we can calculate the electric field, the contribution to the the additional contribution to the electric field due to this polarization. That was what we had done last week. Of course, we didn't yet discuss how do we calculate the polarization to start with, and that is what we will be doing today. And another thing that we had defined was this displacement field, which was given by epsilon 0 times the electric field plus the polarization. Now, the advantage of defining this displacement field is that the equation for the displacement field doesn't really see the material. It only sees the free charges. Of course, the simplification is kind of misleading because this is one equation that the displacement field satisfies, but this is not enough to solve for to find the displacement field in the general case. But of course, if we have a system that is quite symmetrical, like you can have a point charge in a uniform dielectric medium, or a sphere in a uniform dielectric medium, or a system that has some rotational symmetry, like the cylindrical symmetry or the spherical symmetry, in that case, this would be enough to determine the displacement field. But in general, we also need to find the curl of the displacement field if we want to solve it generally. So unless we are in a very special case, these equations doesn't really help much. Without knowing the properties of the material, we cannot really proceed further. We need to somehow model our medium. Now, any questions before we continue? From the newcomers? Questions? Now, the problem is, how do we determine this polarization? It will be, different materials will have different properties in the way that they behave under an external electric field. So this relation between the polarization and the electric field will be highly the material dependent. But nevertheless, in most cases, you see, what creates this polarization is the electric field that if you have an atom, if you put it in an electric field, then the charges will be displaced. And the charges will, most of the time, will be basically displaced along the direction of the electric field. So the atom will acquire a dipole moment in the direction of this electric field. Well, a matter is a collection of atoms. So for most materials, at least, the displacement of these positive and negative charges will be in the direction of the electric field. And furthermore, it will be proportional to the electric field. So we define this quantity This chi E is called the electric susceptibility. Well, this doesn't always work. But for quite a number of materials, it does work. And if for a material this expression is valid, then we call such a system as a linear dielectric. Now, why doesn't it work all the time? Well, let's see. Consider some molecule, not a simple atom, but a molecule like the carbon dioxide. We have the carbon here, oxygen here, and another oxygen over here. Now, if you apply an electric field in this direction, parallel to the axis of your molecule, the polarization parallel to the axis will be easier. You see, there's all this length of the molecule that the electrons can move. So this polarization will have some value. Epsilon 0 E, if you apply an electric field parallel to the molecule. But if you apply an electric field perpendicular to the axis of the molecule, well, the atoms will not be able to move that much, the electrons and the nuclei. So the polarization perpendicular for this susceptibility in the presence of an electric field perpendicular to the axis, in general, will be different. In general, they will be different. So if you apply any electric field, not necessarily parallel to the axis, not necessarily perpendicular to the axis, you can always divide it into two parts, one parallel and one perpendicular to the axis of the molecule. But this tells me that the polarization that I will obtain will be epsilon 0 chi perp E perp plus epsilon 0 chi parallel E parallel. Absurd. Since these two, if these two are different, you cannot take them in a common factor. So you cannot write this as a term proportional to the electric field. It will have a different direction than the electric field in general. So we do have, in fact, if you think of a crystal, for example, a crystal is basically made up of layers. And it will be easy to polarize the crystal, let's say, along the layer, but it will be harder to polarize it perpendicular to the layers. So again, in this case, this susceptibility will not be just a number. The polarization will not be just the electric field multiplied by a number. But in this course, we will restrict our attention to linear dielectrics only. So we have this. So another thing to pay attention to, this E over here, well, it's kind of this relation, although it looks quite simple, it is in fact quite a complicated relation, because this E over here is not really the electric field that we apply. It's not the external electric field. It's the total electric field. It's the total electric field that will determine the polarization of your material at a given point. So this total electric field has the external electric field plus the electric field created due to polarization. So you apply an external electric field, it creates a polarization. This polarization modifies the electric field, and hence this modified electric field modifies the polarization. So you have all this. If you just go step by step, you have this infinite series. All of it is summed up in this relation. Now let's come to the displacement field. We know the polarization. This was the epsilon 0 times the electric field plus the polarization. This is equal to epsilon 0 times the electric field plus, now we have the polarization is epsilon 0 times the susceptibility times the electric field. which is equal to epsilon 0, 1 plus the electric susceptibility times the electric field. So this is our displacement field. And this epsilon, you see up to now we always had this epsilon 0, but now we define this new constant epsilon, which is epsilon 0 times 1 plus this susceptibility. This is called the permittivity. Do you know the meaning of being susceptible? Yatkın can be influenced by. So you see this, we call this susceptibility because it measures how easy it is to polarize a given medium. If you have a larger susceptibility, that is your material is easily influenced by the electric field, then you will get a larger polarization. So that's why we call it the susceptibility. And if you look at this definition of the permittivity, you see that epsilon 0 is nothing but the permittivity of a medium with 0 susceptibility. So that's why we have that 0. And these constants, the susceptibilities, permittivities, are some things that you can actually measure. They are tabulated, so you can just look at in the books. Also in your book there is a table. Look up their values. So we can consider these permittivities and susceptibilities are constants that are known. So if you know your material, you know the corresponding susceptibility. Once you know the susceptibility, now we will be able to solve our equations. We already know this relation. We also had this relation of the electric field. Curl of the electric field should be 0. But before, we didn't know how to relate these two. You see, if you want to solve for a vector field, you need to know the divergence of the vector field and also the curl of the vector field. You have to know both of them. But up to this point, we only knew the curl of the electric field and divergence of the displacement field. But now we are able to relate them because the displacement field is nothing but epsilon, the permittivity, times the electric field. So if you just put it in the divergence equation, divergence of epsilon times E, this is equal to rho free. Now we know the curl of the electric field. We somehow know the divergence of the electric field also. So we can determine the electric field uniquely using our boundary conditions. So let's start with a infinite uniform dielectric. So if we have an infinite uniform dielectric, it basically means that this permittivity is just constant everywhere. Well, just pay attention that here, I didn't take this epsilon out of the divergence. I kept there on purpose because we will see many cases that epsilon is in general not a constant. It will be position dependent. If it is position dependent, when you are calculating this divergence, you have to also take the derivative of the epsilon. Now, if we have an infinite uniform dielectric, in this case, well, it is constant, so I can take it out of the divergence. So we know that the curl of the electric field is equal to 0. That is always true whether you have a medium or not. And then the divergence of epsilon times E, which is now epsilon times the divergence of the electric field, which is equal to rho free. So the divergence of the electric field is rho free over epsilon. You see, before we didn't have any medium. In that case, divergence of E was equal to rho over epsilon 0. But plus the curl of E is always 0. But we already have written down the solution of this equation, so it will be the same over here, with the identification that instead of rho, we have rho free. Instead of epsilon 0, we have epsilon. So the electric field is nothing but in integral form, d cubed. The electric field at the point r is the integral over the charge density, 1 over 4 pi epsilon. Epsilon is position independent, so I can take it out of the integration. R minus r prime divided by r minus r prime cube. We can determine the polarization. Remember, polarization was defined in terms of the electric field as epsilon 0 times the permittivity times the electric field. Well, this is nothing but 1 over 4 pi. Well, epsilon was epsilon 0 times 1 plus the electric permittivity times epsilon 0 times the electric permittivity. We also have this integral. Now, the bound charge due to this polarization was defined as minus the divergence of the polarization. But this is equal to epsilon 0 chi e divided by 1 plus chi e times minus the divergence of 1 over 4 pi epsilon 0 d cubed r rho free cube. But now this integral over here basically is exactly the electric field that this free charge distribution only will create. We know the divergence. The divergence of an electric field is equal to the charge density divided by epsilon 0. This is equal to epsilon 0 chi e 1 plus chi e minus rho f over epsilon 0. So these epsilon 0s, they cancel. So basically the bound charge density minus this ratio times rho free. So basically the charge is reduced by the medium. And the total charge that creates our electric field, which will be the free charge plus the bound charge, this will be equal to 1 over 1 plus the permittivity times the free charge. So basically what happens is, let's say, rather than putting a charge distribution, let's assume you put one point charge in your dielectric. And if you measure this electric field created by this point charge, it will be as if it is the electric field created by a reduced charge. Let's say you put a Q charge at a given point. The electric field will be the electric field created by the total charge, which is the free charge that we put over there, plus the bound charge that is induced due to this polarization of the medium, and that the total charge will be just this fraction times the charge we have. So the observed charge will be less than the charge that we had actually put there because of the effects of our medium. So this is rho free plus minus chi E divided by 1 plus the permittivity times rho free
N'in divergence rho free bir epsilon 0 dedik eğer bu free anlatma hangi rho?
Which one? The one on the right.
Evet.
This is true if there is no medium. So there is no bound charge. This is the total one or the free one or whatever you want to call it. Or if there is medium, you will still have this equation, but this rho will be the total charge density. Not the free, not the bound. Remember this distinction between the free charge, the bound charge, and the total charge. The free charge is the charge that we put over there. Plus there is the bound charge. These are the charges in the atoms and molecules making up the matter. It's not the charge that we put there, but once we put our charge, it will modify the charge distribution in the medium and hence create an additional charge density that we didn't put. So that is what we call the rho bound. The electric field is always created by the total charge density, which is the total charge density is the charge density of the charges that we put there plus the bound charge density.
Şimdi biz dedik yani observed charge işte bizim koyduğumuzdan daha az gözüküyor free'den. Ama burada elektrik field'da da free charge kullandık.
But you see, this is epsilon 0. If you open this up, this is epsilon 0 times 1 plus the permittivity. So basically, the electric field is created by the free charge divided by 1 plus the permittivity. That is what we had obtained at the end. So we have these three, we are always talking about these three different charges. Rho F. This is what we will call the free charge density. These are the charges that we put. So we can put it, we can take it away, we can just move them around. Those are the things that we control. Then we have rho B. This is called the bound charge density. These are the charges of the atoms, molecules of the medium. They are already there. They just move based on what the free charge we bring. So you bring some rho free, it creates an electric field. That electric field we'll call the bound charges to move. The charges that already exist in our medium, they will move around, and hence they will modify the electric field also. The net electric field will be created by the free charge that we brought and the bound charge, the redistributed bound charges. And then rho tot, or just rho. This we define as rho bound plus rho free. So this creates the electric field. Rho F is the one that creates the displacement field. So these are basically the summary of the new fields and the densities that we will be talking about. Any questions on these?
Rho formülü hesaplarken divergent oradaki hani direkt rho böyle epsilon zero yazdık ya. Yukarıdaki elektrik fiyatı ama epsilon zero nereden geldi? O zaman epsilon olması gerekmiyor muydu?
Now, I just looked at this expression over here mathematically. Not really from a physical perspective, but just from the mathematical perspective. If in empty space, in vacuum, we have this charge density given functionally by this function over here, then the electric field that this charge density will create will have this integral times 1 over 4 pi epsilon 0. Okay, here there will be epsilon 0. So this is the electric field created by this rho f in free space. So if we take the divergence of this expression, it will be equal to rho f over epsilon 0 in free space. We will have the permittivity of free space because this is the electric field that it would create in free space. That's why I have this epsilon 0. Or another way is you can just, for example, take the divergence. It is with respect to r. I'm sorry, here the integral is with respect to r prime. These are primed coordinates. The divergence is with respect to r, so this is the only r dependence. If you take the divergence of this, it will give you the Dirac delta. You take the integral, this is at the point r. So the bound charge density at the point r is proportional to the free charge density at the point r. Other questions? Let's do an example. Let's just assume we have a point charge in a medium with dielectric constant epsilon. What is the potential at the point r? Well, to calculate the potential, we need the electric field. Because the potential at the point r is nothing but minus the integral from r0 to infinity of the electric field. So if we can determine the electric field, we can determine the potential at this point. Oh, sorry, not infinity r. Later on, I will assume that r0 is at infinity. Plus, of course, there is also the v of r0. So this is the general definition of the potential at a given point. It's just this integral from r0 to r plus the potential at the point r0. It's just a constant that you can choose. And at least if we have a uniform medium, an infinite uniform medium, the problem is not really modified from the previous parts that we had studied in vacuum. The only difference that we have to do is just, instead of epsilon 0, we have to use epsilon. Instead of the permittivity of free space, we will be using the permittivity of this medium. So we already know the solution. The electric field is 1 over 4 pi epsilon times r over r cubed times q. This is our electric field. Well, for a point charge, we also know the potential. V is equal to q over 4 pi epsilon 1 over r. Now, again, instead of epsilon 0, I just used epsilon. Which, by the way, we can also write in this form. Q over 4 pi epsilon 0 times 1 over epsilon 0 times 1 over r. Now, the reason why I wrote it in this form is, one, this is the potential that we would have in the absence of the dielectric. So let us just call it V0. Again, V0 is the potential that my point charge creates at the point R if it was in vacuum. Then, of course, we have this factor over here, which we usually define as epsilon R. This is called the relative permittivity. So if you have a dielectric, what happens is the dielectric reduces the potential by this factor epsilon r. Now, that is kind of expected, because if you apply an external electric field, the polarization will be such that there will be an electric field created in the opposite direction. So the total electric field will be less than the electric field that you would obtain in the absence of the dielectric. Well, if the electric field is smaller, basically this integral gets smaller. So that's why the potential drops. Well, if you just apply this principle to a parallel plate capacitor filled with a dielectric, with dielectric constant epsilon, you see we had defined this capacitance as Q over V. Q is the charge in one of the plates, V is the potential difference between the plates, and C is the capacitance. But we had just seen that put a dielectric basically lowers the potential, so it increases the capacitance. So this is equal to Q over V0 divided by epsilon r. So C is equal to epsilon r times Q over V0. So the capacitance, if you put a dielectric, increases by this relative permittivity. So what did I do wrong? I have one mistake. Well, not mistake, it will still be correct, but I did one step without justifying it. What is it that I used in this derivation, but I didn't really justify it? Where? Well, here I said that the potential at a given point is the potential that I would have in the absence of this dielectric divided by epsilon r. And I defined epsilon r to be the relative permittivity. Well, what I did assume is, for a given charge distribution, for a given total charge, I'm assuming uniform, well, it will be uniform because the dielectric is uniform. The charge distribution will not change whether I have put a dielectric or not. At least the free charge distribution will not change. So this Q will create an electric field, let's say E0. When I put a dielectric, I said that E0 over epsilon r. And I justified above. Or did I? What is this conclusion? I mean, here I obtained the result for what kind of a system? An unbounded, infinite, homogeneous system. Well, here well, it's still unbounded, it's still infinite, but it's not homogeneous. I didn't put any dielectric here. The previous one was infinite, but this one is not. Infinite in all directions. And only in that case, I can say that the electric field is just, it just looks like the electric field created by only the free charges, with the only modification that epsilon 0 should be replaced by epsilon. This is true only if I have, let's say, an infinite system. But here, epsilon, at this point is epsilon 0, this is vacuum. Here I have a dielectric, it's epsilon, it's not constant. So how can I still use the same expression? Well, you see, if this has finite length, in that case, I have to assume fringing effects. But I can assume that it's infinite in this direction. But still finite in this direction. So if I assume that the plates are infinitely big, so there is no fringing effect. But almost, you seem to be on the right track. I assume the absence of fringing effects in this derivation. So what is the electric field here? 0. It will stay 0. So even if I put a medium over here, it will not be polarized. So whether I have these infinite plates in an infinite medium, infinite in all directions, or I have an infinite plates with dielectrics only in between, they will be exactly the same because outside these plates there is no electric field. So I can still use the results of the previous page. I can use this result over here. Because in the regions where I have an electric field, the dielectric is uniform, and effectively it's infinite in every sense. Well, let's calculate the energy stored in my system. Well, this is what I will be assuming. Let's say I have a system that has dielectrics, and I'm bringing rho free. So what will be the energy stored in my system? how much work should I do to bring rho free from infinity to their final positions. So what I do is I just take rho free, divide it into very small bits, and take each bit, each very small bit one by one. So to bring each one of these bits, I have to do an energy, I have to do a work. By this much. So I bring a very small delta rho f of the free charge. There's already a potential in the system. Let me call it V. And then I have to do this for all the charges. Integrate over all the volume. Well, I will also add this 1 over 2. Do you remember where this 1 over 2 comes from? If you remember, we could have two approaches in calculating the energy. Either we bring one charge, calculate the potential at the point that we brought it, then bring the other charge, calculated the potential that the charges that are already present create at that point. We bring the third charge and to a point and multiply the charge with the potential created by all the charges that we brought previously. So in that case, we don't have this 1 over 2 factor. Or the other way of calculating exactly the same thing was take one charge, multiply that charge with the potential created by all the other charges, V, and sum over all the charges, but this time, to avoid the double counting, we have to divide by 1 over 2. So that's where we have this 1 over 2. Well, you see, rho f d cubed r is already my d cube.
Yani biz bu rho f'i komple mi getiriyoruz yoksa küçük küçük mü?
You see, there are these two different approaches, as I said. One is we just bring it one by one, all the charges. But in this case, you multiply the charge with the potential created by all the previous charges. In that case, you don't have this 1 over 2. Or the other approach is look at your charge distribution. All of them are already there. Take one charge, multiply that charge by the potential created by all the other charges at that point. Take another charge, multiply that charge by the potential created by the other charges at that point, and do this for all the charges. But in this case, you have to add that 1 over 2. Well, now I know what rho f is. Instead of rho f, I can just put the divergence of this displacement field. V is the potential still. Now I can write this as the divergence of the displacement field times the potential minus the displacement field times the gradient of the potential. I just use the derivative of this product. Derivative of this product will be the divergence of d times v, that is what I want, but there will also be an additional term d times the gradient of v, that is the term I subtract. Well, the first term is just the surface integral of the divergence times v over the boundary of my volume. And then I have 1 over 2 d dot e. Well, assuming I have an infinite dielectric, I can easily set my volume is infinite, the boundary will be at infinity, so this term doesn't contribute, and I'm left with the other term.
Şu
Can you say why there is no contribution from the system?
I'm assuming the surface is at infinity. If the surface is at, I have some free charges over here. They will create a displacement field which will go to 0 at infinity. So the displacement field, well, that's the surface integral, sorry. Well, there is one point that you have to pay attention to. Okay, this term goes to 0. The integrand goes to 0, but the surface goes to infinity. So you actually have this indeterminate limit, 0 times infinity. But the displacement field, very far away from your localized charges, it will go to 0 as 1 over the distance squared. V will go to 0 as 1 over the distance. So this product will go to 0 as 1 over the distance cube, or the radius of your surface cube. But the area of your surface will increase with the radius squared. So the product of d times v times the area will behave like 1 over the radius of your volume. And as the radius goes to infinity, it just goes to 0. Now at this point, remember the corresponding expression we had for in vacuum. We had delta W was equal to 1 over 2 epsilon 0 E squared. Well, if you want, we can still do the same thing. Remember, D is equal to epsilon times E. If you have a linear dielectric, in this case, the work done will be 1 over 2 epsilon times E squared, or 1 over 2 epsilon times the integral of D squared. So this is the energy stored in a dielectric. Now, before you go for a break, well, we had obtained this relation already. And we said that whatever charge distribution you have, independent of your charge distribution or where your charges are, this is the total energy stored in your system, always. But now we calculate the electric field, and we get this relation, which is definitely different than that one. But you see, in this case also, even if we have matter or material, the system is just a collection of charges, which create electric fields. And the energy stored in the electric field is always this one. Now, what's wrong? What's the difference between the two? Well, if epsilon is equal to epsilon 0, they do match. But if epsilon is not equal to epsilon 0, they don't match. What's the difference? Why is there a difference? Because remember, that expression over there that we derive for charges in vacuum, well, every system you can treat as charges in vacuum.
How charges makes resistor breaking just from this?
So?
That's why we need to do a different program in order to store the same amount of charge.
Well, kind of. You see, that expression over here is the work that we have to do to bring all the charges from infinity to their final point. Whereas this one over here assumes that our dielectric is already there. The dielectric is there. We are not bringing the dielectric from infinity to there. We are only bringing additional free charge. So that's why these two expressions, although both of them are correct, they just refer to different things. This is the energy, the work that we have to do to bring all the charges, including the bound charges, into their final position. That is the work that we need to do in order to bring only the free charges from infinity to their final position. So for example, if you have just a dielectric without any electric field inside, external electric field without any free charges, for example, for this one, this gives me 0, because since there are no free charges creating the displacement field will be 0. Whereas this one will not be 0, because although I'm not exerting any external electric field, although the average electric field is 0 everywhere, if you look at very precisely the electric field between the atoms, you will see that the electric field is non-zero, and this total energy will be different from 0. But this energy is not what we are actually interested in, because this will always stay as it is unless I break it. What I'm interested in is what happens if I bring some additional charges here, or what happens if I take this to some other place where I have an electric field, an additional electric field, etc. How much work should I do in this case? So in that case, this is the expression I need. Okay, any last minute questions? So see you after 10 minutes.